Today, I want to talk something about central limit theorem, and there's so much of hype on limit theorem. This people think it's profound. Um, a lot of patterns in universe is based upon the distribution that results from central limit theorem, which is known as often called normal distribution or Gaussian distribution. But what the heck is central limit theorem? Um, and before we even think about what central limit theorem is, I think it's nice to visualize it in terms of what's really happening when we talk about central limit theorem, and it's not that profound, to be honest, and that's what I'm trying to do here. um, Imagine this. Imagine there's a lot of balls. There are some big balls, small balls, and all sizes of balls, and circles of a lot of things. And some are small, some are small, some are medium, and some are big, and some are huge. Let this that be. Let that be a huge one. Now, um, if you try to arrange them all on a chart, um, and this would be the number of items, or it's called frequency, and this would be the sizes of bars. um, you'll know that the small ones, say there are five small ones, so there's five small ones, one, two, three, four, five, um, and then a little medium ones, probably it's about one, two, three, four, and then a little bigger one, probably more, a little bigger one, probably like very less. You may get all kinds of patterns, and a large one, probably three of them. You don't know. I mean, it's just you get a pattern of random distributions. You don't know which one is bigger and which one is how many of them are how many. So in essence, you got this distribution. Now, what if you what if you kind of what if you take a mean of that, a mean of this, and then you probably think that, oh, okay, this is the mean. And what's the mean? You clump them all together, and you get this giant ball with all of this smaller and bigger and all sizes of balls together, and then you divide that by the number of balls. So you break it down into number of balls, and you break it down, and finally you get a size which we call as mean. All right, so that's the mean. Now you got this mean of the things. Now what is central limit theorem is that you take a sample from this. So the number of samples, probably you take five items, 5 bars per sample, and take a mean of it, mean of sample, and plot. All right, so let's do that. So you took 5 samples, you took the mean of it, and the 5 samples, let me take it from here. All right, let me divide this chart before that into three, just 3 areas. All right, 3 areas. This is the mean. Let me divide into 3 areas. So this is area 1, this is area 2 from here to here, and this is area 3 from here to here. All right, so these are three areas. Sorry for my um, rough drawing here, but you know, it's to get a sense of what it is. Now, I'm gonna take five things, all right? Now, let me choose five things. So, let me check the small balls. So, let me tell 1, 2, 3, 4, 5. So, and then I take a mean and I get a small mean here. Now, I expect you to ask me a question, or at least probably some of you might have thought about that. Why the hell did I choose only from here? All what I'm asked to do is take five randomly. I could have taken one from here, one from here, one from here, one from here, one from here. Why did I always choose five from here? And then I got mean here. And that's exactly what the central limit theorem is. That if you pick five things randomly, there are chances that you'll pick one from here, one from here, one from here, not always from one this same kind of thing. And if you had if you've even picked four from this area and then you had one big one in that mix, the mean would come somewhere in between this, because this is, you're clumping up one big with four small, and then you get a medium sized one when you break it evenly. So the chances are that when you pick things from here, when you pick things from here, when you pick things from here, the chances are that there will be a lot of stuff in the middle, because you're picking from all from here, here, here. And whenever you pick from a big and small, the chances are you get a medium one, right? And that is the reason that there will be a lot of things in this medium area. In this medium here, you'll get a lot of things just because you are picking a lot of things across. And whenever a large thing meets a small one, you get a medium. Whenever you get a medium and a small one, again, you get somewhere in between. And remember, you're always picking five things at a time. Five is a random number. If you pick two things at a time, you may not get a normal. So this is called normal distribution. All right, this is called normal distribution. Right now, so this is means of sample. This is the frequency. So this, each item here is mean of the samples, or in other words, this is, we took five, so this is the mean of five things taken randomly. For this to happen, it's very rare. You got to choose all the five small balls to get this one. To get this one, it's also rare because you got to choose all the large balls to get this. But this to happen, it's very easy. It's very easy. There's a lot of room here. It's very easy because you choose this and this. If there's at least one of the large in a combination of small, you get here. So it's very likely that you get something over here, because when you pick, it will be mostly a mix of things. Now one may ask that, oh, when you pick something in random, it's independent. It's equally likely that I pick all of this, equally likely that I pick this and next from here and next from here, to what is likely to pick from here, then here, and then here. So how does it matter? And that's a confusing part here. But the thing is, it's not about, it's really not about the likelihood of picking things from here or here. The thing is that when you take a mean of things, when you take a mean of things, if there is a mix of large and small, it comes to the medium size. And that's why there are more medium things comes when you do repetitions over and over and over again, that you expect that there's a lot of medium things. I hope it was clear. I mean, it's kind of hard. It's not easy to understand and grasp. And that's because of the confusion which I just mentioned, is that, you could think that, oh, why not you take five balls, for five small balls, and take a mean, which would be a small. The likelihood of getting this is same as I pick small, small, big, small, small, then you get a medium. So why there are more this one, why there are more medium than smalls? Because you can likely pick anything, right? The thing is, just by having one large in the combination, you'll get this. But if it's all small, you'll get small. So the thing is, when you do it many, 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 many times, there is a chance that out of five you randomly pick, a lot of them will have a combination of this and this. And that's the reason you get something in the middle. All right. I'd like to hear your comments and your thoughts about this. And this is as simple as it is. So, what's profound in it? Um, it's just nothing profound. It is just because the mean is calculated in a particular way. Mean is just combining everything together and breaking them up equally, and you get a reasonable size, which is we call it as mean. And just because mean is been calculated that way, we get something like this. So yeah, and many other function, I think, which is like a mean, would also produce a distribution like that. So it's nothing strange. It's just the way things are.